With that, I am happy to introduce Dr. Justin Schoof, Director of SIU's School of Earth Systems and Sustainability and Professor of Geography and Environmental Resources. Justin, over to you.
Okay, thank you. So I'm sharing my screen. Can everybody see the screen now?
Yes.
Okay, so thank you, Amy, for the invitation, and to the other organizers and participants. It's nice to see you all here. What I'm going to be talking about today is an overview of climate science, and specifically with some implications for Southern Illinois. Now, many of you have probably become aware that very recently we had a new IPCC report released on the physical science of climate change. And I want to start with just a couple of, kind of summary points. So what are the main takeaways for this talk? Well, first of all, the new IPCC report really just includes stronger statements about many of the things that were in previous reports. So from a climate science perspective, there's not really a lot that's there that's new. It's just stated with greater confidence and greater understanding in many cases. So the key takeaways are, first, the current climate is the warmest in the history of modern civilization. Human activity is the dominant driver of observed warming in the last century. Our understanding of climate change is not based on some single data source, but emerges from consideration of lots of sources. So we have land-based measurements, marine-based measurements, et cetera. So we don't have to rely on one source, but rather we see a holistic picture when we look across different data sources. The magnitude of changes beyond the next couple of decades really depends strongly on global greenhouse emissions, and therefore on our willingness to reduce emissions. Climate change impacts are already occurring and vary by region and season. I think we've all become acutely aware recently with some events that the signal is certainly emerging from the noise when we look at climate change and its associated impacts. So if we think about our region in the context of resilience, what do we think might happen here? Well, the expected impacts for us include things like increasing summer heat stress, which we would expect to have an impact on productivity. That's especially true for outdoor workers. We expect to have warmer winters, which will reduce human stress, but is likely to have negative impacts on fish and other recreational interests. We expect shifts in agriculture. That is, if we don't have any adaptation, yields will be quite a bit lower than they are today. And we also expect increases in energy demand that will be associated with higher costs and, of course, issues related to reliability. And the last thing I want to say before really getting into the climate science is that we really have two paths to address the situation that we're in. We have mitigation and we have adaptation. So mitigation means taking action that would avoid the climate change happening in the first place. So you could think about reducing carbon footprint, for example. But then we can also think about adaptation. So adaptation is about what we might do to prepare for climate change that we already know is in the pipeline. So for example, right now along the Gulf Coast, there's a lot of interest in adaptation and what kind of changes might have been made in the aftermath of Hurricane Katrina to avoid similar tragedy in the wake of Hurricane Ida, which we're now all quite concerned about. So this is what the global temperature record looks like. And from this record, you can see that there's quite a bit of variability, but there's also a lot of warming that's happened. So if we look over the last 100 years or so, 140 years, what we really see is about 1 degree Celsius or about a little over 1.5 degrees Fahrenheit of warming. It doesn't matter which data set we look at, we see a similar type of record regardless of the data set. So that doesn't matter too much. Now, interestingly, we can think about what might have caused the temperature change that we observe. So this is a figure from the new IPCC report. And what you can see is the observed warming on the left. You can see again about 1 degree Celsius with a little bit of error bar on that. But where did that warming come from? So if you look at the middle plot, you can see the total human influence basically matches the observed warming. Now, how does that work? Well, we have effects from greenhouse gases, right? Like carbon dioxide, methane, and so forth. Those are these well-mixed greenhouse gases. But then we actually have some human influences that cool the climate. So for example, the effect of aerosol pollution actually has a cooling effect. So that when you add the aerosol pollution with greenhouse gas warming, you actually get something that's in the middle, and it matches the observed record actually quite well. Now, that's not to say that there's no natural variability or natural component to the change. There is, but it's just far outweighed by the human contribution. So that in the end, what we see is that the human impact on climate more or less matches the observed change. So in other words, when we say how much of the observed warming are humans responsible for, the answer really is just about all of it. So we see that CO2 is the primary culprit on this figure. Methane's a big one too, but it doesn't stick around quite as long. So carbon dioxide gets most of the attention. And so this is what our carbon dioxide records look like at our longest instrumental record, which is at Mauna Loa in Hawaii. A couple of things to note: the increase is nonlinear, so it's accelerating. In other words, this year's increase will be a little bit larger than last year's. Pre-industrial concentrations were around 285 parts per million. So you can see 285 parts per million, say around 1750, maybe even close to that in 1850. But by the time we get up to 2020, we're somewhere between 410 and 420 parts per million. To put this in context, atmospheric CO2 concentrations only differ by about 90 parts per million between glacial and interglacial periods. So the type of change that we've invoked in the system is similar to what you would expect between a glacial and interglacial cycle. It's just that it hasn't had the time to respond to that magnitude of a change. And lastly, current atmospheric CO2 concentrations are higher than they have been any time in the last million years, and likely much, much longer. So Earth's average near surface air temperatures increased by about 1 degree Celsius since the late 19th century, and the majority of that warming has resulted from human activity. We can see this when we look at the figure. You can see that a lot of the warming has actually happened since the 1970s. We're now warming at a rate of about 0.2 of a degree per decade, which is pretty remarkable. Globally, the 10 warmest years on record, well, they're just listed here: 2016, 2020, 2019. You start to see a theme. All of the warmest years on record are very, very recent. Even 1998, which was a tremendous record when it happened, is no longer even among the 10 warmest on record. So we might ask, how has our local and regional climate changed, and how will it change in the future? So I'm going to show a couple of figures. These are the trends locally in air temperature. And so the figures show it in degrees Celsius per decade with the color bar shown. And then what I'm looking at is on the top left, we have the annual trend. And then on the bottom, we have the trend for winter, spring, summer, and autumn. And you can see what the trends are for Carbondale. If you look there in the box, you can see them in degrees Celsius or degrees Fahrenheit per decade. So at the annual scale, we've actually warmed quite a bit. The cell for Carbondale in this data set has warmed at about 1/4 of a degree Fahrenheit per decade. This is a 7-decade data set approximately. So we're talking about 1.75 degrees of warming Fahrenheit at the annual scale. But you'll notice that it's actually strongest in the spring. So that in spring, we've actually warmed by about 2.25 degrees over that 70-year record. One thing that you'll also notice here is that we haven't had very much warming in the summer. So the cell over Carbondale actually is warming, but a lot of the Midwest has a very weak warming trend or even a slight cooling trend. And there's a lot of interesting science about that. Now, interestingly, a lot of the warming has been in the minimums. So if you look at the annual mean daily maximum temperature, you can actually see that we haven't warmed very much at all. But if you look at the annual minimum temperature, we've actually warmed quite a bit, about 0.5 degree Fahrenheit per decade. So the minimum temperatures are increasing faster than the maximum temperatures. And what that means is sort of that the daily range is decreasing. Another really remarkable thing is the frost-free season length. So the length of time between the last freeze in the spring and the first freeze in the fall, on average for Carbondale, that's around a little under 200 days we go without a freeze. And the trend in that is really remarkable. So if you look across the entire Midwest, you see these strong positive trends. For Carbondale, that's about 4 days per decade. which means over this 7-decade period approximately, we have nearly an extra month of summer that we didn't used to have. We can think about warm extremes as well. Interestingly, in our area, because of our lack of warming in the summer, we actually have low agreement in terms of the extreme temperature changes. Now, when we look at precipitation, we see kind of a different story. So this is the same figure as the one we looked at a few minutes ago, but now it's for temperature. And you can see that over most of our area, we've seen an increase in temperature. We would actually expect this with warming. And it turns out to be about an inch extra per decade. And again, that's pretty remarkable when you think about a 7-decade data set. Our average precipitation here is about 45 inches per year. So we're talking about 7 inches more than we would have gotten in about 1950 on average. Now, in terms of changes in extreme precipitation, and I probably should have explained this, but this is another figure from the latest IPCC report where they've tried to say something about regional changes. So these hexagons sort of represent areas of the world. So this is Central North America, Eastern North America, et cetera. And in this case, you can see that we do have some confidence related to an increase in heavy precipitation, and that confidence would be considered medium over the central part of North America. And in other words, we're confident that it's attributed to human activity. So in terms of the historical climate, we know that we have a tendency toward warmer conditions in our region in recent decades. The greatest warming is outside of summer. That's actually limited the impact of heat on human heat stress from a temperature perspective. It turns out the humidity is actually increasing, so that offsets some of that. We have the greatest regional warming in minimum temperatures, and we have a very large increase in the frost-free season length that's resulting in longer summers. I actually have a PhD student right now, Yao Xue, who's working on this as part of her dissertation. In terms of precipitation, we know that we're seeing wetter conditions in our area in general, with the largest trend during spring. And also we have some medium and increase in confidence in the extreme precipitation trend and its attribution to humans. It's important to note that the observed changes that I've described are consistent with what we expect from theory. So for reasons that I won't go into in the interest of time, we expect if greenhouse gases are causing the change, that we would have greater increases in Tmin than Tmax and so forth. Okay, so in terms of thinking about future climates, I was going to talk a little bit about how we construct them, but I'm going to just skip over that in the interest of time and show this figure. So this is another figure from the latest IPCC report. And what we're showing here are future projections. So how warm do we expect it to be this century? And of course, this depends a lot on what we do. So we use what are called SSPs, or shared socioeconomic pathways. So for example, we now have SSP1, which is a sustainable path. You can see that SSP1 produces much lower temperature changes at the end of the century than some of the other ones. SSP2, middle of the road, all the way up through SSP5, which you would think of as being fossil fueled development or taking the highway, if we want to compare it to the green road. And these result in temperature changes anywhere between, we stay at about 1.5 degrees, right? So this is like Paris agreement kind of stuff. And then we get way up here to stuff that is really, truly very scary to think about. Now, interestingly, change is not going to be the same across the world. So one of the things they've done in this new IPCC report is they've tried to say, instead of looking at changes, say, in the 2050s, let's look at changes when the models show 1.5 degrees of warming. So if you have 1.5 degrees of warming at the global scale, this is what we would expect the pattern to look like. Notice that the land areas warm by a little bit more than the oceans, and that we also have some Arctic amplification. Both the southern hemisphere and the northern hemisphere polar regions warm faster. Notice that this is just exaggerated as we go to higher and higher levels of warming, but that if we're getting 4 degrees Celsius of warming, that we're going to have some areas, particularly land areas and high latitude areas, that are going to warm considerably more than 4 degrees Celsius. So one of the things that we might want to think about is how climate might change in our region. And one of the reasons we might think about extremes is because they're always a lot more impactful than averages. So I'm going to just show you a couple of projections that we developed in a recent paper. And I'm going to show you frost days, which are days below zero, where the minimum temperature gets below zero. In other words, you might actually expect some frost to form on days like this. And then tropical nights, which are those nights where the temperature stays above 20 degrees C. And when that happens, of course, we don't get very much relief if we're in the middle of a heat wave. So these are those really, warm summer nights. And these are the days that would produce a frost. So here's an example. This figure on the left shows the mean number of frost days across our region here in Southern Illinois. So Carbondale's right in this area. And then you can see in this figure that Carbondale gets on average somewhere around 100 frost days per year. This is kind of a non-mitigation approach. So we just keep using fossil fuels as we have. We kind of maintain the status quo, business as usual, if you will. And in this case, we end up with about 45 fewer frost days per year than we have now. So the implications here are for things like then getting late frosts, which of course are incredibly damaging to our local fruit crops. In terms of tropical nights, we see kind of a similar thing where across Southern Illinois right now, we're getting 30 to 40 of these nights per year where the temperature doesn't get below 68 Fahrenheit at night. In the future, according to these projections, we stand to see about 65 more of these. So we go from having 35 of these tropical nights per year to having about 100 of them per year. So that's a major increase in heat stress. Okay, so a couple of summary points. The global climate and the climate of Illinois have changed considerably in the last several decades, and with high confidence, they're going to continue to warm in the coming decades. The warming here has been greatest at night and outside of summer. We will be warming in the summer. We are warming in the summer, and we do expect greater heat stress. We've also experienced changes in precipitation, including greater extremes in most locations. The magnitude of future warming at large scales depends on mitigation strategies, right? We really need a global effort in order to do this. So we're talking about reducing greenhouse gas emissions. Because we're locked into some warming, regardless of our mitigation efforts, we also need to be ready to adapt. Adaptation measures, by the way, are good practice even in the absence of climate change. So I will leave you with that. I hope I've left time for a couple of questions, and I look forward to hearing from the other panelists. Thank you.
Thank you, Justin. I'm torn between saying that was uplifting and terrifying.
We have choices. It demonstrates that we really have choices. And, we're locked into some impacts from climate change, but we have great choices in front of us about how serious those impacts have to be.
Yeah, I think that was a big point of this last report, is that, these things are happening. There's a certain amount, there's nothing we can do about it, but the choices we make in the coming years are going to determine the impact over the long term. So really it is right now that's going to be a big thing.
Well, if you're paying attention, you've probably heard things about increases in extreme precipitation. And just in the last week, we had a 17-inch daily rainfall in Tennessee that I can't believe it wasn't a bigger news story. I mean, there's a lot going on in the world right now, but there were, I believe, more than 20 fatalities and maybe still a couple dozen people missing. And this was barely even a headline. New York City, with about 140 years of record, recorded their wettest hour on record last week in Central Park. So we're starting to see the signal emerge from the noise. In other words, we shouldn't be thinking about climate change and things like extreme precipitation increases as something that's not it's going to happen. It is happening.
Right.
And what we're seeing now is like the tip of the iceberg. So if we think that these events are extreme, at 1 degree of warming, it is a bit terrifying to think of them at 4.5 degrees of warming. Now, I'm an optimist. I don't think that we're going to have 4.5 degrees of warming. I think that we will find some solutions. But certainly, I think even the types of events that we're seeing now are very concerning in terms of stretching the limits of the system.
Questions in the chat box.
Okay, I'm gonna read those real quick. And so just real rapid fire, okay, Justin?
Sure.
So the first question is the CO2 increase the main cause of climate change?
Yes.
Okay. Do local mitigation strategies have the ability to impact local climate changes, especially temperature and precipitation extremes?
Yes, they do. So for example, many of you have probably heard of the urban heat island effect. So the types of building materials that we use, the amount of green space and blue space in urban areas can really make a big difference. Even Carbondale, with our small population and relatively small town, do have a urban heat island of about 1.5 to 2 degrees under some types of weather conditions. So in the middle of a heat wave, that 1 to 2 degree difference can be very substantial.
Right. Okay, how long do you think we can avoid the climate disaster in our area with no changes?
I don't think we're avoiding it now. I think
oh,
it's already happening. And, you know, we spend a lot of time thinking about like 1.5 degrees, 2 degrees, 2.5, 3. One of the real things that came out of this latest report is that every additional amount of warming is associated with additional impact. There's no magic number that we stay below that. We have no impacts. We have impacts now, and every additional bit of warming is going to result in additional impact.
okay, next question. Is the minimum temp increasing more than the max more concerning?
Well, it kind of depends. I mean, they're both increasing. And I didn't go too far into this, but, you know, greenhouse gas warming is all about reducing heat loss. And that heat loss happens at night. That's why the minimum temperatures are increasing faster. We're minimizing the amount of heat that can escape at nighttime more than we are during the day. And so it's changing the daily temperature range like this, but they're actually both going up. It's just that the minimums are going up a little faster. They're not going to catch the maximums or anything. We don't have to worry about that.
Okay, well, we have lots more great questions, and I apologize for not being able to get to all of them. But Justin, thank you so much. That was very informative. Awesome to learn all that stuff and to know that you're on top of that. And thank you again for being here. And are you going to stick around? Maybe we can ask you questions later.
I am going to stick around at least for a bit.
Okay, thank you.
Thanks.